Welcome back to Makaut Smashers. Today we begin our computer architecture series with fourth semester. So the chapter 1, Introduction to Computer Architecture. This chapter lays the foundation for understanding how computers are designed and optimized for performance. We will revisit the basic architecture concepts and explore the quantitative techniques and learn how performance is measured and reported. Understanding these topics is crucial for building the efficient computing system. We will also discuss the instruction execution and performance benchmark, which play a key role in evaluating a processor's speed. So, whether you are preparing for exams or enhancing your technical knowledge, this video will provide a solid introduction. Make sure to watch till the end to grasp these essential concepts. Don't forget to like, share, and subscribe for more informative content. Now, let's dive into the computer architecture. So, now, review of basic computer architecture concept. Computer architecture defines the design and the functionality of computer system, focusing on how components interact to execute the instructions efficiently. The three key aspects are instruction set architecture, you already know from computer organization, micro architecture, and system architecture. So, ISA serve as the interface between software and hardware. ISA means instruction set architecture. It is the interface that works between the software and the hardware, determining how programs communicate with the processor. Microarchitecture refers to the internal design of the CPU, including the execution units and pipeline stages. The system architecture covers the components like the memory, I/O devices, interconnects. Understanding these levels helps in optimizing the performance, power consumption, and cost. Computers process instruction in a cycle like the fetch, decode, execute, and write back. So the efficiency of these operations impacts the processing speed. Different architectures such as RISC, reduced instruction set computing, CISC, complex instruction set computing follow different design philosophies. Modern processors integrate multiple cores and parallel execution units for enhanced performance. So studying these concepts helps in designing the more efficient computing systems. So quantitative techniques in the computer design. Quantitative analysis is essential for evaluating and improving the computer performance. It involves, you can say, measuring the parameters like the clock speed, instruction throughput, and execution cycle. Performance is often analyzed using the equation you can see in the screen, the CPU execution time. The low CPI and higher clock speed result the faster executions. From the mathematics point of view, you can see the designers use the Amdahl's law to estimate the performance improvement when enhancing the specific system components. The law states that speed up is limited by the portion of the system that cannot be improved. Another key metric is MIPS, millions instruction per second, which measures the instruction execution speed. However, MIPS can be misleading because it does not consider the instruction complexity. Flops, floating point operations per second is better measure for scientific computing. So analyzing these metrics allows the engineers to make the informed decision on optimizing the CPU design. So in the formula, the instruction count IC, it is the total number of instruction a program can execute. The cycles per instruction CPI, the average number of clock cycles required to execute one instructions. Some instruction take more cycles than others, you can say. The clock cycle time, the time taken for one clock cycle to complete. It is the inverse of the CPU clock speed. So now, measuring and reporting the performance. Evaluating a computer's performance involves benchmarking and real-world testing. Benchmarks are standardized programs designed to test the processor's efficiency under different workload. Popular benchmarks are the SPEC, Standard Performance Evaluation Corporation, for general computing, and LeanPack for floating point calculations. So performance metrics include latency, means response time, throughput, task per second, and power efficiency. Real world applications such as video encoding or AI inference helps to access the practical performance. Reporting performance involves analyzing the multiple factors, including the energy consumption, thermal output, which impact the system design. Power performance trade offs are essential for mobile and embedded systems. So, speed up ratios help to compare different architectures. IPC, instruction per cycle, is another critical metric showing how efficiency a processor execute instruction per clock cycle. So by analyzing these metrics, designers can optimize the hardware for specific applications like gaming, AI, data processing. Understanding this technique is essential for evaluating and improving the computer system. Overview of instruction execution and performance benchmark. Every computer program consists of a sequence of instructions that must be executed efficiently. The instruction execution cycle follows four key steps: fetch, decode, execute, and write back. Modern processors enhance the execution through pipeline, branch prediction, and parallel processing. Different type of instructions such as arithmetic, logical, and memory operations impact the execution speed. Performance benchmark help to evaluate how efficiently a CPU handles the real world task. Benchmarks like you can say SPEC, int, SPEC, FP, it measures the integers and floating point performance. The TPC, Transaction Processing Performance Council, evaluates the database transaction speed. Geekbench and Kleinbench are widely used for consumer processor comparisons. The high speed or you can say high performance computing relies on flops benchmark, while embedded system focus on power per watt efficiency. So understanding the instruction execution and benchmarking helps in choosing the right processor for a specific workload. Engineers use these insights to design the faster and more efficient computing systems. That's conclude our first chapter on Introduction to Computer Architecture. See, we are merging the two syllabus, the Makaut syllabus and the Makaut organizer syllabus. So after this completion of the series, we will solve numerical questions and also some suggestions for examination, important questions, okay, and PYQ discussion. So today we explored the fundamental concept of architecture, performance measurement, and benchmarking. These principles are the backbone of modern computer design, impacting the processor's efficiency and system performance. In our next video, we will dive deeper into pipelining and performance optimization. So stay tuned for an in-depth breakdown of hazard, pipeline stages, and optimization technique. If you found this video helpful, hit the like button and share it with your friends. Don't forget to subscribe to Makaut Smasher and press the bell icon for updates on future videos. Have any questions? So drop in them in the comments and we will discuss them in the upcoming sessions. So keep learning and stay curious and see you in the next video.